आज हम डिस्कस करेंगे सेंट्रीफ्यूगल कंप्रेसर्स फंडामेंटल्स। आज का टॉपिक ऑफ डिस्कशन है सेंट्रीफ्यूगल कंप्रेसर फंडामेंटल्स, कंप्रेसर वेलोसिटी ट्रायंगल्स, कंप्रेसर हेड्स, कंप्रेसर एफिशिएंसी एंड पावर। फंडामेंटल्स: centrifugal compressor is a machine used for generation of pressure rise in the system. That means inlet pressure, gas enters with lower pressure to the compressor, and when it comes out from the compressor, the pressure becomes more than inlet pressure. So there is a pressure rise. आप यहाँ देख सकते हैं, दिस इज कंप्रेसर। ये कंप्रेसर का इनलेट है और ये कंप्रेसर का आउटलेट है। Similarly, this is the profile for compressor. So this is inlet guide vane, and gas comes in here and then it goes out. There is a diffuser here, diffuser guide vane. Similarly, you can see the flow path of the gas. This is inlet guide vanes. So gas is entered axially to the impeller and coming out radially. You can see gas comes in axially और ये बाहर radially बाहर निकल रहा है. As impeller is spinning, gas is also given centrifugal force, and so pressure rise occurs in impeller as well as there is an increase in velocity. तो यहाँ जो velocity होगा certainly absolute velocity काफी ज़्यादा रहता है. Oh sorry, not this place. I mean exit of the impeller का जो velocity होता है ज़्यादा होता है, and diffuser में velocity कम हो जाता है to gain the pressure. The cross-sectional area of impeller starts increasing from inlet to outlet so that inlet relative velocity starts decreasing from inlet to outlet. Normally 50% head rise और pressure के term में भी बोलते 50% pressure rise occurs in impeller, and kinetic energy at impeller outlet is converted into pressure rise in vaneless diffuser, van diffuser और casing. ये तीन सेक्शन है. ये vaneless diffuser सेक्शन है, this is a van diffuser है, ये वाला casing का remaining portion है. So this is a casing. Diffuser can be vaneless, circular plate होता है, van diffuser and movable diffuser guide vane भी होता है. So there are three types of diffuser. For controlling the flow through compressor, inlet guide vane, उसको short में बोलते हैं IGV, is installed in the inlet of compressor, and sometimes inlet throttle valve, उसको बोलते हैं ITV, is also installed for controlling the flow rate. With the inlet guide vane, gas absolute inlet velocity angle can be changed as per requirement for better control. तो इसमें हम प्री वेल कर सकते हैं, इसमें एक्चुअली कर सकते हैं और ओवरटर्न भी कर सकते हैं इफ यू हैव आईजीबी. पर अगर आईटीवी है तो हम सिर्फ इसमें एक्सियल एब्सोल्यूट वेलोसिटी ही पॉसिबल है. बट इन केस ऑफ इनलेट गाइड वेन all possible velocity can be anything, pre-well or axial or overturn. A compressor has to operate safely in the system, and so anti-surge control valve, उसको short में बोलते हैं ASV, is installed in compressor process to take care of surge control and protection. Function of inlet guide vane and anti-surge control valve is to control the process, or process could be सक्शन प्रेशर कंट्रोल, डिस्चार्ज प्रेशर कंट्रोल एंड फ्लो कंट्रोल. ये तीन टाइप के कंट्रोल नॉर्मली यूज होते हैं कंप्रेसर में. तो आईजीबी और आईटीबी, सॉरी आईजीबी और एंटी सर्ज वाल्व का यूज ये प्रोसेस में यूज होता है. Surge occurs only in centrifugal and axial compressor, and surge is a phenomena when operation of machine is not stable. There is a back and forward flow of gas occurs. In forward flow, pressure rises, and in backward flows, backward flow pressure drops, and this is dangerous and cause the damage of machine if it is not attended just before surge stall occurs, where there is a momentarily stoppage of flow. It is important to note that only partial reversal of flow occurs during the surge. During the compressor surge, vibration of rotor increases and bearing and process temperature also increase. There is a humming sound when machine surges, and so surge control and surge protection system are implemented for safe operation of the compressor. If the flow and pressure rise is more than multi-stage compressor is used. Suppose single stage has some limitation of discharge pressure, तो उस केस में हमको मल्टी स्टेज कंप्रेसर यूज करना पड़ता है to cool to cool the each stage. Intercooler is used, so process cooler is used, and which is to save the overall power saving. Multi-stage compressor can be integrally gear compressor or barrel type. In integrally gear compressor, main bull gear shaft drives pinion shaft where impellers are installed at each pinion shaft. Rotor speed can be chosen based on the gear ratio as per design. Bull gear is connected to main to the motor or steam turbine. Barrel type compressor. In barrel type compressor, all impellers are installed on the single shaft and there is a rotor connected to motor or steam turbine directly or through a speed reduction gearbox. Now compressor का use क्या है? So it is used for petroleum, petrochemicals, oil, gas, LNG, air separation, steel, power plant, and fertilizer. Now let us talk about something about impeller or wheel. Impeller को wheel भी बोलते हैं, तो इसके बारे में समझते हैं. You can see this is the actual impeller, backward leaning vanes. This is inlet, and this is outlet. Same thing is also shown here, and this is beta 2, which is shown with reference to normal or radial, beta 2. Impeller blades can be forward, radial or backward. ये ब्लेड रेड यहाँ बैकवर्ड दिखाया गया है. इट कैन बी रेडियल भी हो सकता है, फॉरवर्ड हो सकता है. बट in compressor industries, only radial and backward leading vanes are used for better efficiency because backward vanes जो होते हैं उसका efficiency अच्छा होता है. Impeller outlet blade angle is designated in two ways. One measure from radial, जैसे अगर हम इसको रेडियल से मेजर कर सकते हैं उसको बीटा 2 बोला. दूसरा टेंजेंट से भी मेजर होता है, यहाँ से भी कर सकते हैं. अनदर वे ऑफ मेजरमेंट इज फ्रॉम टेंजेंट डायरेक्शन, यहाँ से भी मेजरमेंट होता है टेंजेंट से. बट इस कॉन्टेक्स्ट में हम एंगल मेजरमेंट जो भी दिखा रहे हैं वो आपको रेडियल से दिखाएंगे. सो वी कैन कॉल इट इज ए बीटा 2 which is considering from the radial direction. आप इसमें भी देखिए रेडियल ये है तो ये आपका एंगल है, ये बीटा 2 है. Typically impeller blade angle measured from radial direction which is available in compressor industries. इसमें कितने, जैसे 0 डिग्री, ये आपका बीटा 0 है, तो अगर हम यहाँ से मेजर करेंगे तो 90 डिग्री हो जाएगा, तो इसलिए उसको 90 डिग्री में भी दिखाया हुआ है. तो 0 डिग्री रेडियल तो 90 डिग्री टेंजेंट. सिमिलरली अनदर टाइप के जो इम्पेलर होते हैं वो 20 डिग्री रेडियल तो 70 डिग्री टेंजेंट, 25 डिग्री 65 डिग्री 40 तो 50, 45 to 45, 50 डिग्री to 40 डिग्री, 55 डिग्री to 35 डिग्री. So these are the normally type of outlet, type of angles normally available in industries typically. As a velocity triangle जो इम्पेलर में होता है और इनलेट गाइड सॉरी इम्पेलर में होता है वो थ्री टाइप्स में हम दिखा सकते हैं. वन को प्रीवर बोलते हैं, दूसरे को हम एक्सेल बोलेंगे और थर्ड को ओवरटर्न में. तीन को हम देखते हैं. तो इनलेट गाइड वेन आईजीबी इज इंस्टॉल एट सक्शन ऑफ कंप्रेसर. सो इनलेट flow to the compressor can be pre-whirl, axial and overturn. So pre-whirl का देखिए ये एंगल जो है थीटा 1 which is lesser than 90 डिग्री, तो इसको प्री-whirl बोलेंगे. जब थीटा 1 90 के बराबर हो जाएगा तो एक्सियल हो जाएगा, इफ इट्स मोर देन 90 तो ओवरटर्न हो जाएगा. तो इसका वेलोसिटी ट्रायंगल इनलेट, अच्छा वन मोर इम्पोर्टेंट इंफॉर्मेशन, जो वेलोसिटी ट्रायंगल इनलेट का होता है वो एवरेज इनलेट डायमीटर का हम लेते हैं, क्योंकि ये एवरेज लिया हुआ है, नॉट टिप का बट हब का लेते हैं, एवरेज का लेते हैं। जो भी हम वेलोसिटी ट्रायंगल बनाते हैं विच इज मेजर ऑन एवरेज डायमीटर। तो U क्या है? इनलेट मीन टिप वेलोसिटी, V1 इज इनलेट मीन रिलेटिव वेलोसिटी, C1 इज इनलेट मीन एब्सोल्यूट वेलोसिटी, CA1 इज इनलेट मीन एक्चुअल वेलोसिटी, CW1 is inlet mean whirl velocity, theta 1 is inlet mean absolute angle which is equal to inlet guide vane angle। तो हमको गाइड वेन का एंगल उतना ही सेट करना होता है जितना यहाँ वेलोसिटी ट्रायंगल से हमने डिजाइन किया। अभी another type of category we can call it inlet velocity triangle axial inlet। जैसे ये अब एक्सेल है, थीटा 90 के बराबर है तो एक्सेल हो जाएगा। Axial inlet of flow is possible in case of installation of inlet throttle। Throttle valve में तो पक्का एक्सेल ही होता है। However, IGB के केस में this is possible। We can design or we can select IGB angle is 0 or sorry 90 degree or X for axial। तो inlet velocity again I said it is based on the average tip velocity, average diameter। तो U1 is inlet mean tip velocity, V1 inlet mean relative velocity, C1 is inlet mean absolute velocity, CA1 is inlet mean axial velocity which is equal to C1। तो एक्सेल के केस में CA1 is equal to C1 हो जाता है, बट वर्ल कंपोनेंट जो CW1 जीरो है, इसमें कोई वर्ल कंपोनेंट नहीं है, एंड थीटा 1 इज, अब सॉरी जीरो नहीं होगा, 90 डिग्री होगा, यहाँ बाय मिस्टेक लिखा हुआ है। तो थीटा जो डिग्री होगा it will be 90 degree if you see from here 90 degree। अभी ओवरटर्न का केस देखते हैं। इनलेट गाइड वैन ओवरटर्न तभी पॉसिबल हो सकता है जब हम हमारे पास आईजीबी है, आईजीबी रहेगा देन ओनली वी कैन डिजाइन overturn case। And but this is not good design I can say, because there is no margin for compressors, क्या बोलते हैं margin, there is no margin for compressors from the design case। So inlet velocity triangle is based on average inlet tip velocity of the impeller। So U1 is inlet mean tip velocity, V1 is inlet mean relative velocity, C1 is inlet mean absolute velocity, CA1 is inlet mean axial velocity, CW1 is inlet mean whirl velocity। थीटा 1 इस केस में आपको 90 डिग्री, सॉरी 90 डिग्री से भी ज़्यादा होगा। एक्चुअली ये यहाँ तक आना चाहिए, दिखाया हुआ नहीं है। It should be more than 90 degree। Theta 1 should be here, not this। Now, outlet velocity triangle without slip, मतलब this is ideal case when there is no slip। So, outlet velocity triangle without slip में देखिए, ये ऐसा outlet relative velocity है, आपका U2 है, और ये जो आ गया absolute velocity without slip है। तो U2 is outlet impeller tip velocity, V2 dash is ideal outlet relative velocity, C2 dash is ideal outlet absolute velocity, CW2 dash is equal to ideal outlet whirl velocity, CA2 is equal to outlet axial velocity। अभी हम outlet velocity angle with slip, अब देखिए चेंज हो जाएगा। outlet velocity triangle with slip consideration में U2 is outlet tip velocity, V2 is outlet relative velocity, C2 is outlet absolute velocity, CA2 is outlet axial velocity, CW2 is outlet whirl velocity, CW2 dash is ideal outlet whirl velocity, and by definition slip factor is CW2 upon CW2 dash, and due to slip the head rise will be lowered। ऑयलर्स हेड राइज, और उसी को इंथैल्पी राइज भी बोलते हैं, बिकॉज ऑयलर हेड राइज एंड इंथैल्पी राइज इज सेम। तो क्या होता है, विद द हेल्प ऑफ वेलोसिटी ट्रिगर ऑयलर्स हेड राइज और इंथैल्पी राइज कैन बी कैलकुलेटेड। सो व्हाट इज ऑयलर हेड राइज और इंथैल्पी राइज? C2 इंटू CW2 माइनस C1 इंटू CW1, वहाँ जिसमें कि U1 इज इनलेट मीन टिप वेलोसिटी, U2 इज आउटलेट टिप वेलोसिटी, CW is inlet mean whirl velocity and CW2 is outlet whirl velocity। इसमें रिलेशन भी है, there is a relation between the isentropic efficiency and isentropic head। क्या है? आइसेंट्रोपिक एफिशिएंसी इज इक्वल टू आइसेंट्रोपिक हेड upon Euler head rise or enthalpy rise. Similarly, polytropic efficiency is equal to polytropic head rise upon Euler's head rise or enthalpy rise. Now we'll discuss about the compressor work head or head. There are three types of head: isothermal, isentropic, and polytropic head. So isothermal head rise occurs in compressor where temperature is constant. तो उस केस में isothermal head rise होगा HI is equal to Z1 into R by M into T1 into log P2 by P1, where HI is isothermal head rise, P1 P2 is inlet outlet pressure, T1 is inlet temperature, Z1 is inlet compressivity factor, M is molecular weight, and R is universal gas constant. Isentropic head rise, where entropy remains constant and it is considered as an ideal condition. Isentropic head rise Hs is equal to Z1 into R upon M into K upon bracket start K minus 1 bracket close into T1 into bracket start P2 by P1 to the power bracket start K minus 1 bracket close upon K minus 1 bracket close, where Hs is isentropic head rise, P1 P2 is inlet outer pressure, T1 is inlet temperature, Z1 is inlet compressibility factor, K is average heat capacity ratio, and M is molecular weight, R is universal gas constant. Now polytropic heat rise is also expressed in HP is equal to Z1 into R by M into N upon bracket start N minus 1 bracket close into T1 into bracket start P2 by P1 to the power bracket start N minus 1 bracket close upon N minus 1 bracket close, where polytropic index N is equal to log P2 by P1 upon log RD2 upon RD1, where HP is a polytropic heat rise, P1, P2 is inlet outlet pressure, T1 is inlet temperature, RD1, RD2 is inlet outlet density, Z1 is inlet compressivity factor, N is a polytropic index, M is a molecular weight, and R is universal gas constant. Now, stagnation polytropic heat rise is also expressed. Stagnation polytropic head rise HPO is equal to Z1O into R upon M into N upon N minus bracket star N minus 1 bracket close into T1O into bracket start P2O upon P21 P2 P2O upon P1O bracket closed to the power bracket start N minus 1 bracket close upon N minus 1 bracket close, where again, stagnation polytropic index N is equal to log P2O upon P21 upon log D2O upon D2 D2 1 होना चाहिए D2 1 0. So if HPO is stagnation polytropic head rise, P P10 P20 is stagnation inlet outlet pressure, T10 stagnation inlet temperature, RD1 0, RD20 is stagnation inlet outlet density, Z10 stagnation inlet compressibility factor, N is a stagnation polytropic index, M is a molecular weight, R is a universal gas constant. Now compressor enthalpy. Enthalpy rise occurs in compressor as work is done on compressor by the compressor, and this is expressed as work is done on compressor by the compressor. This is expressed as or a static enthalpy rise H is equal to H CPA into T2 minus T1. Stagnation enthalpy rise is HAO is equal to CPA into bracket start T2 minus T1 bracket close plus 0.5 into bracket start V2 square minus V1 square bracket close, where H is a static enthalpy rise, HAO is a stagnation enthalpy rise, T1 is static inlet temperature, T2 is a static outlet temperature, CP is average specific heat capacity ratio at constant pressure, V1 V2 is inlet outlet velocity. इसमें देखिए आइसोथर्मल पोलोट्रोपिक आइसेंट्रोपिक इस सभी में जो मिनिमम है आइसोथर्मल है, पोलोट्रोपिक मैक्सिमम है. Now let us understand compressor efficiency. This is understood. This can be understood as a suppose 120 kilowatt is input power to driver. motor. Then output power of motor driver, let's say 110 based on efficiency of motor. Now power of 110 kilowatt is transmitted to impeller or wheel through the bearing. Say let's say 10 kilowatt का loss है. That means power available to impeller is now 110 minus 10 is equal to 100 kilowatt. Now power 100 kilowatt is available at impeller to develop the pressure. Suppose 85 kilowatt power is required in isentropic compression to raise the pressure in compressor, then isentropic efficiency will be 85 upon 100, which is 0.85. In addition, let's say if 88 kilowatt is consumed in polytropic compression, then polytropic efficiency is 88 upon 100, which is 0.88. So polytropic efficiency of compressor is more than isentropic efficiency. If you see isothermal efficiency, isentropic efficiency, and polytropic efficiency, polytropic is a maximum efficiency, isothermal is a minimum efficiency. But in industry, isothermal efficiency is not used, only isentropic efficiency and polytropic efficiencies are used. Now compressor static efficiency क्या होता है? Static isothermal head rise HI is equal to Z1 into R upon M into T1 into log P2 by P1. And static isentropic head rise क्या होगा? HS is equal to Z1 into R upon M into K upon bracket start K minus 1 bracket close into T1 into bracket start P2 by P1 to the power bracket start K minus 1 bracket close upon K minus 1 bracket close. Static polytropic head rise HP is equal to Z1 into R upon M into bracket R upon M into N upon bracket start N minus 1 bracket close into T1 into bracket start P2 by P1 to the power bracket start N minus 1 bracket close upon N minus 1 bracket close. A static polytropic index N is equal to log P2 by P1 upon log RD2 upon RD1. A static enthalpy rise or Euler head rise, we can write H is equal to CPA into T2 minus T1 bracket close. So a static isothermal efficiency, we can write a static isothermal head rise upon a static enthalpy rise. So I is equal to HI upon HA. Similarly, a static isentropic efficiency will be a static isentropic head rise upon a static enthalpy rise. Similarly, a static polytropic efficiency will be a static polytropic head rise upon a static enthalpy rise. Now compressor stagnation efficiency. So stagnation polytropic head rise, we can write HPO is equal to Z1O into R by M into N upon brackets N minus 1 bracket close into T1O into bracket start P2O upon P1 P2O upon P1O bracket to the power bracket start N minus 1 bracket close upon N minus 1 bracket close. So stagnation polytropic index N is equal to log P2O upon P1O upon log RD2O upon RD1. O. Static enthalpy rise, we can write CPA into bracket start T2 minus T1 bracket close plus 0.5 into bracket start V2 square minus V1 square bracket close. So stagnation polytropic efficiency EPO is equal to stagnation polytropic head rise upon stagnation enthalpy rise. Compressor power, stage power is equal to mass flow rate into isentropic head upon isentropic efficiency. Coupling power is equal to stage power plus mechanical loss, and input power is equal to coupling power upon motor efficiency, and motor input power is square root 3 into voltage into current into power factor. So this is input power, which is equal to coupling power plus motor efficiency. This will be same, but coupling power has two segments: compressor stage power plus total mechanical and bearing loss. So thank you for